March 12, 1945. Luftwaffe Test Center, Rechlin, Germany. A captured P-51D Mustang stood in Hangar 5 at the Erprobungsstelle, the Luftwaffe's primary flight test facility. The aircraft had made a forced landing 2 days earlier near Münster after engine failure during an escort mission. It was recovered largely intact by a Luftwaffe ground detachment and delivered under order of the Technisches Amt for immediate analysis. The Mustang's left wing had been damaged by flak, but the fuselage and engine remained serviceable. The aircraft retained most of its internal systems and instrumentation. It was the first fully functional example of the type obtained by German engineers in 1945. At 8:40 hours, the hangar doors were closed and work began. The inspection team consisted of 6 engineers from Rechlin and 2 technicians from Messerschmitt's Augsburg works. Senior engineer Oberingenieur Karl Weiss led the assessment. His task was to identify any aerodynamic or manufacturing principles that might explain the Allied fighters' superiority at high altitude and long range. The men began with external measurements. The fuselage skin was smooth and flush riveted. A gauge showed surface irregularities of less than half a millimeter across the upper wing. Compared with the Me-109G, whose rivet heads disrupted airflow, the Mustang's laminar-flow wing presented almost no surface interruption. Weiss dictated notes for the report: surface continuity excellent. No step-in panel joints. Indicate strict tolerance control. At 9:20 hours, the cowling panels were removed. The exposed Packard-built Rolls-Royce Merlin V1650-7 engine showed clean casting, uniform fastener spacing, and a precision machine supercharger housing. The inspectors noted the use of standardized fittings, identical bolts, and accessible maintenance points. German aircraft often required hand-fitted components. Here, every part appeared designed for assembly line production. One mechanic examined the propeller hub. The Hamilton Standard unit employed an automatic constant-speed control system, hydraulically actuated and electrically governed. The system allowed the engine to maintain optimal revolutions per minute through all power ranges. German variable pitch systems achieved similar results, but required greater pilot attention. Weiss recorded, reduced workload. Simplified operation at altitude. The cockpit was inspected next. Instruments were arranged symmetrically with large, clear numerals. Switchgear followed a consistent pattern. The oxygen regulator, fuel selector, and radio controls could be reached without removing harness restraints. A SCR 522 VHF radio set was installed behind the seat. Tests conducted at Rechlin months earlier with captured Spitfires had shown that VHF transmission outperformed German HF systems in clarity and range. The finding was again confirmed. Fuel system documentation drew particular attention. The Mustang carried an internal capacity of 269 US gallons plus 2 drop tanks of 75 gallons each. The plumbing allowed external tanks to feed directly into the main system before being jettisoned. This configuration extended operational radius beyond 1,600 kilometers, sufficient for escort missions from England to Berlin and return. The Luftwaffe's primary fighters, limited by internal capacity, could not remain with bomber streams beyond Western Germany. At 10:30 hours, attention shifted to the landing gear assembly. The main struts retracted inward and rotated 90 degrees into the wheel wells, achieving a wide stance when deployed. The Me-109's narrow undercarriage had caused frequent ground accidents. The American design demonstrated superior weight distribution and shock absorption. Each component bore identical serial markings, confirming mass production consistency. Technicians measured the radiator intake and exhaust duct under the fuselage. Its variable flap cooling system created a small amount of jet thrust at speed, improving efficiency. This principle had been studied at Göttingen, but not implemented in German production aircraft due to resource constraints. Weiss wrote a single line in his log, "Cooling system contributes to range and performance, elegant solution." By midday, preliminary examination was complete. The aircraft had been fully photographed and its measurements recorded for transfer to Berlin. Weiss summarized his findings verbally to the attending officers. The Mustang, he stated, showed no radical innovation, only exact execution. Every feature served endurance, reliability, and interchangeability. The men agreed that the differences lay not in invention but in production discipline. The team broke for lunch at 12:15. The captured Mustang remained in place on its maintenance trestles, surrounded by measuring equipment and open notebooks. Outside, damaged German aircraft were being towed to the repair area. Inside, the engineers prepared to begin structural disassembly the following morning. What they had already observed suggested that the Allies had mastered not just aircraft design, but the method of building them. The examination of the captured P-51D Mustang at Rechlin occurred during the final weeks of the air war over Germany. By early 1945, the Luftwaffe no longer possessed continuous control of its own airspace. Allied bombers operated in large formations across the Rhine, escorted by hundreds of long-range fighters. The American 8th Air Force, based in England, launched daily missions against industrial centers, transport hubs, and oil facilities. The 15th Air Force, from Italy, struck southern targets. Each force relied heavily on the Mustang to protect bomber streams at altitude. German records from the Generalquartiermeister der Luftwaffe show that between January and March 1945, average aircraft losses exceeded 400 per week. Pilot attrition was equally severe. Even the introduction of the Me-262 jet and Ta-152 high-altitude interceptor could not restore parity. Fuel shortages, disrupted supply lines, and Allied numerical advantage had reduced combat operations to defensive sorties. Against this backdrop, the arrival of an intact P-51D at Rechlin was considered valuable for analysis. The Erprobungsstelle Rechlin had been founded in 1918 and expanded in 1935 into the central testing institution of the Luftwaffe. Its duties included flight performance trials, material evaluation, and comparative testing of enemy equipment. During the war, it had examined numerous Allied aircraft, a B-17 Flying Fortress in 1943, a P-47 Thunderbolt in 1944, and several Spitfire variants obtained from crash sites in France. Most were too damaged to yield complete data. The P-51D was the first example received in operational condition, providing a full opportunity for systematic evaluation. Initial intelligence about the Mustang had reached Berlin in 1943 through captured manuals and pilot reports. Early versions, designated P-51A, had been powered by Allison engines and limited in high-altitude performance. The installation of the Rolls-Royce Merlin transformed the design. The V1650-7 engine, built under license by Packard Motor Car Company, combined two-stage supercharging with efficient intercooling, allowing sustained output above 20,000 feet. Allied bombers typically operated between 22,000 and 27,000 feet, altitudes where German piston fighters began losing power. The Mustang could climb, escort, and return without refueling, a capability no German fighter possessed in equivalent numbers. Reports from the Luftwaffe's Forschungsamt, the research office responsible for technical intelligence, had already identified the Mustang's presence in large numbers over central Germany by late 1944. They noted its use of drop tanks, its endurance exceeding 4 hours, and its ability to engage multiple targets before withdrawing. Rechlin's engineers intended to verify these figures through direct testing. Weiss and his team planned to measure weight distribution, fuel flow efficiency, and aerodynamic performance using wind tunnel data from Göttingen. At the same time, the German Air Ministry was reviewing its own fighter production. The Bf-109K and Fw-190D were improvements over earlier types but remained constrained by engine availability and structural limits. The Jumo 213 and DB605 power plants required meticulous hand assembly, and production had suffered from Allied bombing of factories at Friedrichshain, Regensburg, and Kassel. Statistical reports compiled in February 1945 indicated that U.S. factories produced over 2,000 Mustangs per month, while German output of all fighter types averaged less than 800. The difference extended beyond quantity. American assembly lines emphasized standardization. Components were interchangeable between aircraft built in different plants. Wiring harnesses, instrument panels, and control systems followed unified patterns. German manufacturing still depended on specialized craftsmen, variable tooling, and decentralized subcontractors. Rechlin's engineers understood these realities, but the Mustang allowed them to see the result in physical form. The captured P-51's performance data were cross-checked with Allied air combat statistics collected by the Luftwaffe-Rechlin, the Air Intelligence Service. They confirmed that bomber losses declined sharply after the widespread introduction of the Mustang in early 1944. Between January and June of that year, average daylight bomber losses fell from 8% to below 2% per mission. Fighter coverage had effectively neutralized the Luftwaffe's interception capability. When the technicians at Rechlin began their detailed inspection, they were aware of these numbers. Their purpose was not curiosity but necessity. Every recovered example of Allied equipment was examined for lessons that might extend Germany's defensive capability. The P-51D represented the culmination of American air power, a machine built for endurance, precision, and repeatable performance. For Weiss and his team, the objective was to identify where German design philosophy had diverged and why the difference now determined the outcome of the air war. On March 13, 1945, the Rechlin engineering team began the second stage of the Mustang examination. The objective was a complete technical survey, structure, power plant, and systems, followed by partial disassembly for material analysis. The Air Ministry required all findings to be recorded in standardized form for transfer to the Technisches AMT-GL CE2, the department responsible for foreign equipment evaluation. At 7:30 hours, the aircraft was lifted onto hydraulic trestles. The propeller blades were measured for pitch range and chord ratio. The Hamilton Standard hydromatic propeller displayed uniform machining and perfect balance. Its governing mechanism maintained constant revolutions automatically, reacting to minor load changes without pilot input. German constant-speed propellers, though comparable in theory, required manual fine-tuning. The Mustang's system demonstrated both precision and simplicity. Engine examination followed. The Packard Merlin VE 1650-7 was removed with its mounts intact. The cylinder head showed even coloration, indicating consistent combustion. Supercharger impeller blades were inspected for clearance and finish. Measurements confirmed minimal tolerance variance, a sign of mass production consistency. The two-stage, two-speed supercharger gave the engine a rated output of 1,490 horsepower at 10,000 feet and maintained power above 25,000 feet, performance beyond the capability of the DB605 engine used in the Me-109K. Technicians then analyzed the carburetor assembly. The Bendix-Stromberg pressure injection unit prevented fuel starvation during negative G maneuvers, an issue that had limited early Allied aircraft. The Germans had solved this separately with the Bosch direct injection system, but the American approach achieved similar results using simpler components and easier maintenance. Weiss dictated functional equivalence achieved by production standardization, not design complexity. Attention moved to the airframe. The laminar-flow wing, the most distinctive feature, was dismounted and sectioned. Its main spar was a single extrusion of aluminum alloy, supported by precision-fitted ribs. The surface finish was polished smooth, and rivet heads were countersunk. Airfoil templates taken along the span confirmed the NACA 45-100 profile, thin, with maximum thickness near midchord. This allowed high-speed efficiency but required manufacturing accuracy rarely maintained under wartime conditions. Rechlin had attempted similar profiles on experimental projects, but results were inconsistent. The Mustang demonstrated exact execution of aerodynamic theory in practical form. The fuselage structure revealed modular construction. Sections could be detached for maintenance without disturbing load-bearing members. Electrical wiring was color-coded and labeled. Hydraulic lines followed standardized routing, secured by identical brackets. Weiss noted that such precision would require extensive jigs, inspection gauges, and factory discipline, resources unavailable in late-war Germany. Material samples were taken from skin panels and control surfaces. The alloy composition showed a balance of strength and corrosion resistance. The Germans confirmed the use of 24ST aluminum, equivalent to duralumin, treated for uniform hardness. Surface coatings included a primer layer and a final olive drab enamel, applied by spray in controlled thickness. Paint analysis suggested industrial-scale consistency. The team then studied the radiator and coolant system. The under-fuselage duct employed an adjustable flap controlled automatically by a thermostat. Tests performed with a portable airflow rig confirmed a measurable thrust gain of approximately 150 pounds at 400 miles per hour. This Meredith effect had been documented in Allied technical literature but was seldom applied in German designs. Weiss included it in his report as a minor yet significant contributor to range efficiency. The armament system consisted of 6 Browning .50 caliber machine guns, 3 per wing, synchronized for convergence at 300 yards. Ammunition feeds were belt-driven through chutes with quick-release panels. The installation was simple, accessible, and easily serviceable in the field. A mechanic compared the process to the complex feed arrangements of the FW-190's wing cannon, which required precise alignment and frequent adjustment. The Mustang's layout favored speed of maintenance over sophistication. By late afternoon, technicians examined control surfaces and trim systems. The elevator and rudder were fabric-covered, balanced by aerodynamic tabs. The control cables were stainless steel, coated and routed through pulleys with sealed bearings. Test movement showed minimal friction. These details, while minor individually, indicated a manufacturing culture that valued repeatable precision over improvisation. Throughout the day, data sheets filled with measurements and photographs. Nothing in the design appeared revolutionary, yet each component represented efficiency and coordination. The Mustang embodied an approach where design, production, and logistics operated as one system. Weiss summarized the day's findings in a brief remark recorded in the engineer's log. Every element is built to standard. The result is performance by discipline, not by miracle. On March 14, 1945, the Rechlin team continued its work with focus on performance analysis and comparative data. The goal was to identify operational factors that explained the Mustang's success as a long-range escort. Weiss ordered that each measurement be compared against equivalent data from the Messerschmitt Bf 109K and the Focke-Wulf FW190D09, then the Luftwaffe's most advanced piston fighters. The evaluation began with weight and balance calculations. The P-51D's loaded weight stood at 9,200 pounds with full internal fuel and ammunition. Despite this, wing loading remained moderate, providing stable handling at high speed and altitude. The aircraft's range exceeded 1,600 kilometers with external tanks, nearly twice that of the Mi-109. Charts compiled at Rechlin illustrated that even at full load, the Mustang maintained a climb rate comparable to German interceptors. The conclusion was clear: performance had been achieved without sacrificing endurance. The flight control layout was inspected again for ergonomics. The throttle, propeller, and mixture levers were grouped logically. The pilot's view forward was unobstructed due to the bubble canopy introduced in late 1944 production. In contrast, most German fighters still used framed hoods with restricted visibility. The improvement provided tactical advantage in air combat, especially when escorting bombers where situational awareness was critical. During conference that afternoon, Weiss summarized his observations. "The technical elements are not extraordinary," he stated, according to the stenographic notes preserved in the Rechlin archive. "But the precision and repetition of these elements across production make this aircraft consistently superior." His remark was entered into the official report as part of the concluding section: "The advantage lies in manufacturing method and operational planning." Later that day, the engineers reviewed production photographs obtained through aerial reconnaissance of U.S. aircraft plants. Images of Inglewood and Dallas assembly lines showed hundreds of Mustangs in identical stages of construction. Each airframe appeared uniform, with components interchangeable across lines. German production never reached such standardization. Aircraft built at Regensburg, Wiener Neustadt, or Erla varied in detail, complicating maintenance and logistics. Spare parts often required hand fitting. The Americans had eliminated that problem entirely. At 15:30 hours, material analysts presented results from metallurgical testing. Alloy purity and heat treatment were consistent across samples. Weiss compared these findings to reports from the Reichsstahlfirma et al., which had documented significant degradation in German alloy quality since mid-1944 due to shortages of copper and nickel. Fatigue life in German wing spars had declined by 20% in 1 year. The Mustang, built with stable supply chains, retained full structural reliability under load. The team then examined the service documentation found in the cockpit. The English-language maintenance checklist, though routine, revealed the extent of procedural control. Every system, from fuel inspection to armament loading, followed standardized intervals and recorded verification. Luftwaffe squadrons, by contrast, maintained their own checklists and often deviated from official procedures due to local conditions. The Mustang's documentation illustrated a coordinated system extending from factory to frontline. Discussion turned to operational doctrine. Intelligence summaries from the Luftwaffe's 5. JAG Division noted that American fighter tactics emphasized cooperation and endurance. Pilots operated in disciplined formations with constant radio contact. Engagements were calculated to protect bombers rather than seek individual combat. The Mustang's design directly supported this doctrine: high range, stable flight characteristics, and dependable communication equipment. The German approach, high-performance interceptors launched from dispersed bases had become unsustainable by 1945. By evening, Weiss drafted his preliminary conclusion. He wrote that the Mustang represented the integration of engineering, production, and strategy into one coherent system. No single feature made it dominant. The aircraft's success resulted from industrial organization and predictable quality. His assistant recorded a short statement later quoted in post-war intelligence summaries. "It is not the engine or the wing," Weiss said quietly during the meeting. "It is the method that produced them." The remark summarized what the engineers had begun to realize. The Luftwaffe had pursued technical innovation, jets, rockets, advanced aerodynamics, but lacked the capacity for large-scale implementation. The Allies had pursued standardization, logistics, and pilot endurance. At Rechlin, inside Hangar 5, the difference was visible in every panel, bolt, and rivet of the captured Mustang. When the technical data from Rechlin reached Berlin in late March 1945, the conclusions were already familiar to senior staff in the Technisches Amt independent studies from the Luftwaffe Operations Staff, the Reich Air Ministry Statistical Office, and the Forschungsamt had produced the same pattern. The United States possessed not only more aircraft, but also an integrated system of production, supply, and maintenance that no longer depended on individual factories or specialized craftsmen. The captured Mustang merely confirmed what numbers had shown for months. By 1944, the United States Army Air Forces had achieved a production rate of nearly 1,500 P-51 Mustangs per month. Combined American output of all combat aircraft exceeded 8,000 units monthly. In the same period, total German fighter production, Bf-109, Fw-190, and Me-262, rarely surpassed 1,500 aircraft even under maximum effort. The Allied industrial base in the United States operated beyond the reach of bombing, supported by stable raw material access and automated assembly lines. Germany, under continuous attack from the 8th Air Force, faced chronic shortages of aluminum, high-octane fuel, and skilled labor. Records from the Jagerstab, the fighter staff established by SPE in 1944, illustrate the disparity. Attempts to centralize aircraft production increased short-term output but introduced severe logistical strain. Subcomponents were manufactured across hundreds of dispersed workshops to avoid bombing losses. Transport between them depended on railways already damaged by Allied attacks. Production quotas were met on paper, but many aircraft left assembly plants incomplete, lacking radios, instruments, or gun sights. Rechlin's technical officers knew that even perfect design could not overcome that fragmentation. The Mustang's structure embodied the opposite approach. It had been developed under the Army Air Forces Material Command at Wright Field, with continuous coordination between engineers, manufacturers, and field units. The result was interchangeability. Any component from an Inglewood aircraft could fit a Dallas aircraft without modification. Maintenance manuals reflected that standard. Spare parts were pre-packed, coded, and distributed through depots following the same logistics system used for trucks and tanks. The Luftwaffe relied on limited depot capacity and individual ground crews trained for specific aircraft marks. Operational statistics confirmed the outcome. By February 1945, the 8th Air Force maintained more than 1,500 Mustangs in continuous service, covering bomber formations from takeoff in England to targets in eastern Germany and back. Fuel supply lines through Britain and France guaranteed steady operations. German interceptors, restricted by fuel shortages, could only launch for brief engagements. Synthetic fuel plants at Luna, Politz, and Blechhammer had been bombed repeatedly. Jet fighters, though advanced, were grounded for lack of kerosene. Wehrmacht intelligence summaries also recorded the scale of pilot training differences. The United States graduated more than 9,000 fighter pilots in 1944. Germany trained fewer than 2,000, many with limited flight hours due to fuel conservation. Replacement rates could not sustain combat attrition. The Mustang's endurance and reliability extended the survivability of its pilots. German units replaced entire rosters within months. From Berlin's perspective, the captured aircraft at Rechlin represented the visible result of an entire industrial philosophy. Weiss's report, forwarded on the 27th of March, 1945, described the P-51D as technically conventional but exemplifying complete standardization. His findings were appended to a broader analysis from the General Quartiermeister der Luftwaffe, concluding that Allied control of logistics and manufacturing determined the air war's outcome more than individual performance metrics. The Technisches Amt requested a comparative chart illustrating aircraft availability versus operational range. The table showed that in the last quarter of 1944, American fighters could escort bombers to every target within the Reich, while German interceptors operated within 300 kilometers of base. Even the Me-262 jet, though faster, could remain airborne for only 1 hour. Strategic mobility had become decisive. The Mustang allowed continuous pressure, the Luftwaffe could only respond locally. Within Rechlin itself, testing continued for documentation purposes. No effort was made to replicate the Mustang's design, there was neither time nor material. The engineers compiled final photographs, alloy analyses, and performance graphs for archival preservation. Their conclusion matched the operational reports. The war in the air was decided not by innovation, but by organization. By the end of March, the Rechlin Center faced evacuation orders. Soviet forces were approaching from the east, and most testing activity was transferred to Bavaria. The captured Mustang remained under guard, awaiting transport that never came. Its inspection had confirmed what headquarters already knew, that technical excellence was meaningless without the means to reproduce it in thousands. When Allied forces reached northern Germany in April 1945, Rechlin Airfield was already abandoned. Most experimental aircraft had been destroyed to prevent capture. The P-51D Mustang examined in Hangar 5 remained intact but grounded, its fuel drained and documents removed. Soviet troops entered the facility on the 3rd of May. They recorded several damaged aircraft and engineering instruments, along with partial files from the Technisches Amt. The Mustang's fuselage was later transported east for further study by Soviet aviation institutes. The last official German report concerning the captured Mustang was dated the 29th of March, 1945. It carried the file reference GLC E2NR 245145 and the signature of Oberingenieur Karl Weiss. The summary stated, "No decisive technological superiority identified. The advantage lies in precision, standardization, and operational integration." It was the final technical memorandum completed under the authority of the Luftwaffe before the war ended. Post-war interrogations of German engineers conducted by the U.S. Air Technical Intelligence Group in 1946 confirmed these observations. Weiss and other Rechlin personnel described the Mustang as a conventional aircraft executed with exceptional manufacturing discipline. They noted that the design's effectiveness depended on an industrial system capable of uniform output, continuous supply, and coordinated maintenance. American investigators used these testimonies to assess the efficiency of U.S. wartime production methods. Data from Allied strategic studies later quantified what the Rechlin team had recognized in isolation. Between January 1944 and May 1945, American escort fighters flew over 200,000 sorties across Europe. Bomber losses in daylight raids dropped by more than 70% within 6 months of the Mustang's full deployment. German aircraft losses, recorded by the General Quartiermeister, exceeded 33,000 for the same period, with fewer than half replaced. The Luftwaffe's operational strength declined irreversibly. For the engineers who had examined the captured fighter, the significance was not emotional but analytical. The Mustang represented an engineering culture founded on repeatability and resource control. Every measurement they took, rivet spacing, alloy consistency, hydraulic pressure, and component weight, pointed to a production system that Germany could no longer maintain under wartime strain. In interviews years later, Weiss stated that the aircraft demonstrated what industrial stability could achieve when design and logistics worked as one. Archival correspondence from the British Air Ministry's technical branch, reviewing captured German documents in 1946, echoed that view. A memorandum marked TA Report 21646 summarized the German analysis. Enemy engineers concluded that the American success lay not in individual performance characteristics but in collective reliability. The Mustang embodies the principle of mass precision. This assessment circulated among Allied design bureaus and influenced post-war standardization policies within NATO aircraft projects. At Rechlin, the Mustang's inspection had also served another purpose. It became a case study in the limits of innovation without structure. Germany had introduced the first operational jet, advanced radar systems, and guided missiles, yet could not produce them in sufficient quantity or maintain their field reliability. The United States, using conventional technology but organized logistics, achieved air supremacy through volume, endurance, and sustained coordination. When the Rechlin archives were later examined by Allied investigators, they found the Mustang file among hundreds of technical records on foreign aircraft. The notes were concise, devoid of speculation. Each line recorded a measurable fact: wing profile, surface finish, fuel range, structural weight. Together they described not just an airplane, but a method. By the time these findings were reviewed in Washington and London, the war had ended. The Luftwaffe no longer existed, and the skies over Europe were under Allied control. The P-51D, once an object of technical curiosity in a German hangar, became a symbol of industrial capability that outlasted strategy and design ambition alike. The conclusion entered in the final paragraph of the Rechlin report was brief and unemotional. The aircraft type P-51D confirms that technical success depends upon industrial organization. Air superiority is achieved through production consistency, not through individual innovation. It was a statement based on measurement, written by engineers who had seen the evidence firsthand. Their examination of a single captured Mustang provided the final technical explanation for a war already decided in the air.